Okay, so we're going to sort of make this a bit more abstract, make it a bit more pure maths, and we're going to go and look at least squares and think about in terms of subspaces and vectors. So everything so far, it's always been matrices. We've got, y equals x, beta, and x is this design matrix. And that's basically how you're going to do it in the computer. That's how we do it in R, that's what we're focused on. But I want to think about it in a different way. We know, as I said, that the same model can have different model matrices. So when you think about your design matrix, you could have a categorical variable, and you could either use the reference level or the zero sum. Different matrices, but they have similar interpretation. So the question is, can we put this at a higher level so that each of these individual matrices are just seen as one aspect of that? So what we're going to ask is, what is the unique definition of a linear model? So you get away from matrices and think about it in terms of a higher abstract notion. So we're going to look at linear algebra, we're going to look at vector subspaces, and then we're going to put everything in terms of subspaces. And actually, if you think about it, this means we can actually do linear regression on much more complex objects than what we actually have. But we're not going to go that far. We're just going to show that even though we go to the abstract, everything we've seen still fits within that. So let's start and think about what we mean by a subspace. So first of all, let's set up, that's a weird symbol there. That should be x to the n. I have no idea where that, sorry, r to the n. That's not an n there. That is weird. But anyway, r to the n. So we're going to define basically Rn. By Rn, we're thinking about this n-dimensional Euclidean space. And basically, it's going to be all vectors of length n, where each of the elements are from R, the real numbers. So they go from minus infinity to infinity, and we've got everything. They're a real number. So that's all we're thinking about. And of course, I could take two of these vectors and I could add them. And the way that we add them is we take the first two elements of each one and add them. The second two elements of each one, add them all the way down. So we're doing an element-wise addition. And you can do this addition for any n-dimensional vectors in Rn. We can also do scalar multiplication. If I have a scalar, a, which is a real number, I can multiply that by our vector x. And all I do again is I do an element-wise multiplication. So I take the first element, x1, and I multiply it by a, and I continue that down all the way down to xn. We also can define a thing called an inner product. And what does inner product do? An inner product is designed that it will take two vectors and it will return a real number. So there's a couple of ways we could denote that. We can denote that as x dot y. But if you think about it, that is exactly the same as taking x, transposing it, so instead of it being a column, it now becomes a row, and multiplying that by y. So you take the first two elements, multiply them, the second two elements, multiply them, the third elements, multiply them. Keep doing that till the nth elements, multiply them, and then you add them all together. So that's the summation as I goes from 1 to n, xi, yi. And this can be used to define the norm, which is the idea of the length of a vector. So we denote this by our two lines, which are called verts. And basically what this is I'm going to take the dot product of x with itself and take the square root. So I take each element, square it, add them all up, and take the square root. And we call that the norm. So when we want to do the Euclidean distance between 2 points, we basically do x minus y. We can do minus because if we can add and we can do scalar multiplication, we would take y. We would multiply it by minus 1 and then we'd add these two things together. And then we'd take the norm, the length of that, and that would give us the Euclidean distance. So it would be x1 minus y1 all squared plus x2 minus y2 all squared plus all the way to xn minus yn all squared. Add them all together and then take the square root. The other thing is we can have this concept which is going to be really useful of what we call orthogonal or perpendicular. So if you take the dot product, so you go x dot y, okay, and that gives you a number. You then take that number, you divide it by the norm of x and the norm of y, okay. So you've normalized it by their distances. You get basically the cos of the angle between them, theta. And we're going to say that the vectors x and y are orthogonal or perpendicular if x dot y equals 0. So basically they're at right angles to one another. They're at right angles in this n-dimensional space. And we write this as x, and this is called perp y, x perp y. So we're saying that x is orthogonal to y, and hence y is also orthogonal to x. They're at right angles to one another. So now we're going to define a vector subspace. So we've got some subspace of Rn. So you've got this big Rn, and we're taking a collection of vectors within that. So we've got this collection of vectors, which denote by M. And we're going to say this is a subspace, a vector subspace, if I can take any two vectors in this space, this subspace, I can multiply them by any real number, add them together, and still get another vector that's in the same space. So basically this subspace is closed under scalar multiplication and vector addition. And that's it. So you can take any two vectors and you can try and take a linear combination of them, and the resultant thing is still lies in that subspace. If that's the case, if this is what happens with this set, we call it a vector subspace. So here's an example. I'm going to call it M1, which is in just R3, so it's in three-dimensional space. And the form of every vector in M1 is that it has any real number for x1, any real number for x2, but it's always 0 in x3. That I can multiply that, any two of those, by any real number, add them all up, and you'll still have something of the form of a real number, and a 0. Simple as that. The one more important to us is, consider this. I've got X as an n by p matrix. So it's got n rows and p columns, and there's got scalars in there, real numbers. I've got that. And then I'm going to multiply that by a column vector of size p. And the resultant thing y is a subspace. So basically, if I take a design matrix and multiply it by my betas and I get the y, that y is a subspace. So this is the first time where you can see why I'm interested in subspace, because basically the y we get from our linear model is a subspace. Okay? Next, we're going to define what we call a span. So what do you mean by span? I've gone and grabbed myself p vectors in n-dimensional space. And what I'm going to do is I'm going to look at all the possible vectors I can get by linear combinations of those vectors. What do I mean by linear combination? I can take the first vector and multiply it by a real number, take the second, multiply it by a real number, all the way to the p multiplied by a real number, add this all together, and I get a vector. All the vectors I can achieve from these starting points, so you can think of x1 up to xp as some sort of like ingredients. They're my main things. I can multiply them by real numbers, I can add them all together, and whatever I get, that whole subspace, we're going to call, I sort of jumped ahead and said it's a subspace, you know, it is, but anyway, that whole thing, we're going to call the span of those. So it's like you start with these ingredients, the x1 up to xp, you've got them, and say, right, well, all the vectors I can get from here, and all the vectors I can get from there, we're going to call our span, and we denote that by s of these vectors. So it's always a vector, well, it has to be, because I said, let's think about all possible combinations of multiplied by scalars and add them together. And everything we've got, we kept in the thing. So by definition, this is a subspace, because every time I found I took two vectors and I multiplied by any scalar, add them together, what I got, I then put back in my bag. I've created a subspace by almost definition. And so we say the vectors x1 up to xp is said to span the subspace if m equals that. So if I've got a span of some vectors, and basically you can show that that is equal to our m, then we say that these vectors are the span of the subspace. And we go a little bit further, or we can say, well, let's actually be a bit more precise, because we might have almost doubled up on some of these vectors. If we now choose p vectors, such that they are linearly independent. And what do you mean by linearly independent? Well, remember, one, you can't get any of the vectors as a linear combination of the others. Or the more precise definition is, if I can find a solution in terms of real numbers such that the linear combination of my vectors x1 up to xp equals 0, that will only occur if all the a's are equal to 0, if they're linearly independent. So basically, if I can find a solution to that with at least one of the AI's not equal to 0, they're not linearly independent. But if I can, they're linearly independent. And why that's going to be good, because we're going to say, consider a vector subspace we denote M. We've got a set of vectors, x1 up to xp, but we've added an extra constraint. They are linearly independent, such that these vectors are linearly independent, and the span of them equals M. the space I'm interested in, we say they form a basis of M. Basically, they are the minimum number of vectors I need to get that subspace. Okay? So, for example, if you think about that one right back at the start, M1, where we had an x1, an x2, and a 0, the two vectors I could do to get that is 1, 0, 0, 0, 1, 0. These are linear independent. If I take the dot product, I get 0. So they're linear independent. So they're orthogonal. So I jumped ahead there. Sorry. They are. Well, let's just take it they're linear independent. I cannot find, that was a bit of a jump, sorry. I cannot find at this point a linear combination of those two vectors that will equal 0 unless I multiply them both by 0 first. So they form a basis, they are linear independent, and these will actually give me every vector within that M1. The other thing we've got, and we've been doing this all along, but if I have some vectors x1 up to xp, that I basically are the columns of my matrix X and they're linear independent, they will form the basis for M2, which was that subspace defined by that linear model. Just be careful. Bases are not unique. You can't sort of go set a basis and go, this is it, you can't do better. You can find other bases. Here's an example. This first one, sorry, this should have been a dot point. There's two here. This first one here is another alternative basis for that M1 subspace. And now we've got 1, 1, 0, 1, minus 1, 0. So these are linear independent. They will also form that M1 where you have x1, x2, 0. And also, if I have any p by p invertible matrix X, and I take my X and multiply it by this, that will also form a basis for my linear subspace. Next thing, let's say I have a basis x1 up to xp. And then you come along and go, oh, for this subspace, I also have a different basis, v1 up to vr. If these are both basis for a subspace, the same subspace, we must have the same number of vectors in each. You can't find a way of sort of having, half the number of bases in one compared with another and them still being bases. So in this case, p and r must be the same. And because they're always the same, we've got a name for that. We say that the vector subspace is said to have dimension p if its basis has p elements. So the whole thing when we start talking about dimension of subspace is basically how many basis vectors do I need to make it. Okay, so now we've sort of recapped our basic linear algebra we're going to need, because now we're going to consider linear models as subspaces in the next lecture. See you next time.